Okay, so welcome back. I hope you enjoy your break. And now we have this session on the evaluation of self-healing functionalities and characterization of these materials with self-healing properties. And so we have the presentation of two good young scientists. They both participated in writing the manifesto, so we are very proud of this. So the first speaker is Marta Mirolo. She's working in Grenoble, and so please, Marta, she will speak about methods to evaluate self-healing properties. So please, Marta, the floor is yours. And then do not forget to write questions and questions in the Q&A session, and the answers will be given. Thank you, Marta.
Thank you, Silvia, for the introduction, and thank you for having me here presenting a bit some advanced characterization techniques that we can use for investigating batteries. So before starting, I would like to acknowledge my supervisor, Jakub Netz, who provided me some of the slides that I will be showing today. In fact, here we have a bit of a preview of what I will be showing. So we have different degradation mechanism occurring at the batteries, and we can use different characterization techniques. So this presentation is a bit like targeting the degradation phenomena in batteries, but that's not limited to it, because the same characterization techniques can be used for self-healing, for investigating self-healing properties. In fact, when we look at batteries, we know that they are complicated heterogeneous electrochemical system in which different phenomena that are degradation or self-healing are occurring at different length scale and simultaneously. So, for example, we might have the structural degradation of active material, we might have the formation of voids, we might have lithium dendrites formation, the electrolyte decomposition, all of these phenomena which are occurring simultaneously needs to be investigated from both the material and engineering point of view if we want to improve the performance of the next generation of lithium-ion batteries. And it's important that we study these phenomena in their sample environment because we need to know what is happening during battery operation. And that's why it's important to apply in situ and operando techniques if we want to really understand what's going on and improve the next generation of lithium-ion batteries. So as I mentioned, all of these phenomena are occurring at different length scale. In fact, we can have from the atomic level, for example, active material structural degradation, to the electrode level, in which we have, for example, electrolyte decomposition, we have detachment of active material, binder decomposition, up to the device level, in which we might have, for example, thermal gradient inside batteries during operation. And all of these phenomena which needs to be studied, we need to have different characterization techniques, because we want to have spectroscopy, scattering, tomography. And why is that? Because each of these techniques is giving us different information. So, for example, spectroscopy gives us chemical information about the electrode, about the materials. It gives us mostly collective information. That means that this is coming from few hundreds of micrometer up to millimeter level. So we have information from the whole electrode level, for example. Spectroscopy is mostly surface sensitive, but not only. There are some specific spectroscopy that are applied for having information from more bulk materials. So spectroscopy gives us chemical information. This is not all we need. We also need to know what is happening at the morphological level. So we want to know, for example, if the particles are cracking, if they are detaching. Tomography is based on contrast between materials. So we can see, for example, the difference between active material and electrolyte, active material and conductive carbon, and so on. So we have chemical, we have morphological information. That's not all. We also need to have scattering to gain structural information. So we want to know, for example, during lithiation and delithiation, how the structure of the active material is behaving. So are there modification which leads to inactive phases and so on. Scattering is considered as a bulk technique. So it's pretty much complementary to spectroscopy or to most of the spectroscopy. But thanks to, for example, high energy scattering, what we can investigate is the buried interfaces, for example, in real devices, so in real batteries during operation. So in my presentation, I will give some example for each of these techniques, starting from spectroscopy. So how does spectroscopy, let's say, work? Is basically we have an incident radiation, we have an interaction of this incident radiation with the sample, and this interaction leads to the emission of electrons or photons, and by collecting these electrons or photons, we gain information, gain chemical information from our sample, depending on the phenomena that is occurring. So we can have, for example, X-ray absorption spectroscopy, X-ray photoelectron spectroscopy, X-ray emission spectroscopy. So spectroscopy is a very wide range of technique. It really contains a lot of different tools. So we can play, for example, with the incident radiation, we can play with the interactions, so absorption, photoelectron, and so on. We can play with the detection mode. We can detect electron, photons with different, like, let's say, probing depth, so we can gain real information from the very surface to a bit like deeper in the sample and so on. So by combining all these different spectroscopy techniques, which we can obtain different information about the chemistry of the sample. That's important. We gain chemical information. The example that I will show here is how to investigate, for example, the additive decomposition path. So we had an electrode which is composed of graphite and tin oxide, so it's a composite anode material, which was cycled with a standard electrolyte and with the same electrolyte, but with the addition of FEC additive. And with the FEC additive, there's an improvement in the electrochemical performance of the graphite tin oxide electrode. So the question is, okay, why there's this improvement? Is it the SEI composition that is different from when we use the FEC additive compared to the standard electrolyte? Is it the fact that we are using a composite electrode? So do we have different in the SEI formation between tin oxide and graphite? So what's happening? Why do we get improved electrochemical performances? So we need to have both chemical and morphological information, because we want also to distinguish between tin oxide and graphite SEI formation. So for this study, we decided to use spectrum microscopy, which combines chemical and morphological information. And the technique is called X-ray photoemission electron microscopy. And I will go a bit deeper in explaining this technique, because I know that is a bit of a niche technique. So in fact, this is how a commercial electrode look like. So we all know that these electrodes are complex. They have a high porosity, they have a high roughness, they are composed of different active materials. So in this case, we not only have one active material, but we have a composite. So we have graphite and tin oxide. So we have two active materials. We have some conductive carbon to improve the conductivity of the electrode. We have the binder. We already heard earlier on why the binder is so important in electrodes. And when we insert this electrode into a real operating battery, what happens is that when it's in contact with the electrolyte, we can have different reactivity of the electrolyte with the different component of the electrode. And if you want to understand what's going on at each different of these particles of these materials, we need to have a technique with good which provides us chemical information and which has a good lateral resolution, so that we can distinguish really the different particles. One of these techniques, as I mentioned, is X-ray photoemission electron microscopy, in which we use the soft X-rays produced by a synchrotron to excite the electrons in our sample. The photoelectrons are then emitted by the sample, and they are focused in an electron microscope. And then what we obtain is like images, like an SEM. So we obtain information with a good lateral resolution, with a good surface sensitivity. So we are really probing the very surface, like roughly 3 nanometer. And what we obtain is chemical information as well, because we are probing the transition metal L edges, as well as carbon, oxygen, and fluorine K edges. So we can really study the SEI composition at the different particles in these composite electrodes. So that's what we did. So we used fluorine-free standard electrolyte. So we used chlorine instead of lithium chloride instead of LiPF6. And then we used we looked at the difference between an electrode cycled with the standard electrolyte and with the FEC additive. And then what we observe is that when we look at the decomposition of the solvent, so at the carbonate decomposition, we don't see any difference when we are looking at the graphite and the tin oxide particles. So it means that the solvent, so the carbonate, is decomposing on both graphite and tin oxide. However, when we look at the fluorine K edge and we look at the different active material, then we clearly see that the FEC is decomposing only on the tin oxide. And the fact that the FEC is decomposing only on the tin oxide is probably creating a bit thicker SEI, is probably a bit more flexible, which leads to the improved electrochemical performance of graphite tin oxide electrode when the FEC additive is used. So the next example that I will bring is based on tomography. Tomography is a technique which is used to really like look inside the batteries, inside the materials. It's really like if we are using like magnifying lenses to look inside the battery without having to open it. It's based on the contrast between materials. So for example, if a material is denser than another, then we see a different absorption, and this allows us to distinguish, for example, active material, conductive carbon. We can see the presence of voids or cracks. We can see where the electrolyte is going on, and so on. And then we can use this technique to look really at the whole battery. So from the device level to the nanometer level, in which we can see, for example, the cracks inside the active material particles. So we can really like see the details of the batteries and what's going on. It requires a bit of computation for the image reconstruction, but these are all algorithms that have been developed already. So they are already available for investigating these devices. So the first example that I will present on with imaging is the swelling of silicon. So we already heard that silicon is a promising material for anode, as it has improved specific capacity, with the small drawback of a very large volume expansion up to 300%, which leads to the formation of cracks and crumbling. So this case was this case is exactly what was presented before. So by using different binders, we can study how the binders can accommodate the swelling of this particle. And in fact, this is what, let me stop the video because this is really nice. So what we see here is a silicon electrode during delithiation. So we are removing lithium. So we see the formation of the cracks because the particles is getting smaller. And then during lithiation, the cracks are closing because we are reinserting lithium on silicon. And if we study that with different binders, then we can understand, for example, where the cracks are forming, if they are forming, and this leads to a better engineering for the next generation of silicon-containing electrodes. Another example on based on tomography is what I call killing a battery, because that's exactly the purpose of the experiment. So it's a nail penetration abuse experiment in which we want to simulate what happens, for example, if a car has an accident and some metal parts are penetrating the battery. So how it works, we are just like hammering a nail inside the battery and we are looking at what happens. So in this case, we are the first case, we are looking at a standard current collector. We are like we see the insertion of the hammer at different times, and we take images at the different penetration time. So what we see is that after less than a second, when the nail is penetrating the battery, the electrodes are bending, but then due to the rigidity of the current collector, they are bouncing back. And this bouncing back leads to micro short circuiting, which leads then to the thermal runaway and to the possible explosion of the battery. However, when we look at the same battery, but with a polymer substrate current collector, the electrode during the nail penetration are deforming, but they're not bouncing back. And this leads to the avoidance of this micro short circuiting inside the battery, and hence the avoidance of the thermal runaway, and we obtain safer batteries. If you're interested, like there are plenty of very nice videos on like this tomography on exploding cells, which are a bit disturbing because you are really like killing the battery. You are really like seeing the battery is exploding. It's like a horror movie for me. But they're really nice, and if you are interested, like Google them, and they're really interesting. And then like the last example that I wanted to show is based on scattering techniques, in which we have an incident beam that is interacting with the sample. And then what we look at is the scattered signal. We can look at it in a wide angle or small angle X-ray scattering, in which we look at the structure from the atomic to the nanoscale level. And then what we can see is, for example, we can look at how the active material is changing, how if there are new crystalline phases forming, but we can also look at, let's say, the background, especially when we are using high photon fluxes. So the background contains information. For example, we can look at where the electrolyte is accumulating, as an example. And then we can also look at the small angle X-ray scattering, which gives us information at the nanoscale object, for example, at the swelling of nanoparticles. And that's exactly what we did in this example, in which we are investigating the graphite silicon oxide composite electrode during battery operation. So we are lithiating the composite, we have some relaxation step, and we want to know what happens at the different in the different parts of the electrode. So we have a thick electrode, we want to know what happens close to the separator, close to the current collector, but we also want to know how the graphite and silicon are evolving in time. So during battery operation, we want to know where the lithium ions are, what they are lithiating. Are they lithiating the graphite? Are they lithiating the silicon? What happens during relaxation of this composite? So to study these composite materials, we performed quasi-simultaneous wide angle and small angle X-ray scattering. So wide angle X-ray scattering is, let's say, what we know as X-ray diffraction. So we can study the lithiation of graphite via let's say the peak position of the graphite. Graphite is crystalline material, so it's very easy to investigate. And we can also look at the silicon lithiation by looking at the evolution of the small angle X-ray scattering signal. So when we do this simultaneously or quasi-simultaneously during battery operation, then we can really see in time where the charges or where the lithium is moving between these two materials. And as I mentioned already, like in space, so at the different position in the electrode. As I mentioned, this let's say presentation is mostly on degradation phenomena, or how to investigate the degradation phenomena, but it's not limited to that, because we can also study self-healing properties using this the exact same techniques. It's important, especially for the self-healing, to study the batteries in situ or operando, because we want to know what happens in real time during battery operation. It's important also to combine different techniques at multi-scale, so that we have really like all the information, so chemical, structural, and morphological information at the different levels, so from the particle to the full device, to the full batteries. And another thing is that we can also perform, let's say, long-term studies. So what is possible is to investigate the battery during the first few cycles, and then set the battery aside, let it cycle, for example, for 1000 cycles, and then look again at how it looks like with, for example, when the self-healing properties or functionalities have been kicked in. So we want to know what happens after like long cycling. And this is possible having reproducible positioning systems which are available. The last thing is that I would like to advertise this project, which is the Remade, which I think this is like the good audience for that, because this project is for circular economy, is a platform, is a characterization platform. So if you have any question that, for example, you don't know why your self-healing function is working, or you add a binder and you don't know why it's actually improving the electrochemical performance, Remade give you access to a wide range of techniques for understanding your improved system. So if you're interested, the call for proposal is open, so have a look at their website. And with that, I would like to thank you, and I hope none of you fell asleep during the presentation, and if you have any question, I would be very happy to answer or try to answer to your questions.
So thank you very, very much, Marta, for the very seminal presentation. So it gives the floor to many questions for sure, and opens to many applications. So please take your question in the Q&A, and then we give the floor to Wendy Yudi, I hope I pronounce correctly or almost correctly your name. So very sorry for that, Andy. And then after the Wandy presentation, we will open for Q&A for both of the two presentations. So Wandy is also working in the Department of Chemistry in Uppsala University. Also, he's one of our young scientists of this big community that I'm sure that after this seminar and will increase, because it's very important to have you all connected. And he will speak about the characterization of self-healing polymers. So please, Wandy, the floor is yours.
Thank you very much, Sylvia, for giving me the opportunity to present this interesting topic on the characterization of self-healing polymers. First of all, I want to check if you could see my screen clearly.
Sorry, yes, we can see it well. Thank you. Forgive me. I was muted.
All right. Yeah. So during yesterday's and today's webinar that has been presented by other presenters, we have learned like many new knowledge that the self-healing materials are like very promising for battery applications. Also, many like examples of materials that have like self-healing properties have been highlighted for different like applications in the battery components, including for electrode binders, polymer electrolytes, separators, interface layers, and also artificial ACI layers. However, the existing self-healing materials that have been introduced for like battery applications still cannot fully address the current issue related to the long-term stability of the cycle performance, sustainability, safety issue, and resource efficiency of the battery technology. So we need to perform further development and design of better self-healing materials, which is very important to enable us, to enable the self-healing ability and the practical applications in the battery technology. And in order to get to that goal, the characterization of the self-healing materials is very important to enable us proving the self-healing functions of materials, which includes to see the chemistry and the properties of the materials that we use for this purpose. Also, the characterization will help us to understand the mechanism of the self-healing process, whether the self-healing process takes place similarly or differently in the battery system and outside the battery system. Also, the characterization will help us to evaluate whether the self-healing chemistry effectively works in the battery systems over time against some notorious factors that usually happens in the battery systems during operations, like mechanical stress, chemical degradation, and thermal cycling. And lastly, the characterization will help us also to optimize the systems of the battery, and we can design better self-healing materials in order to achieve these main goals. Self-healing functionalities that we use in the battery are expected to prevent failures in the battery components, which in turn, we expect that it will extend the lifetime of the batteries. And also remember that the self-healing functionalities also can improve, but not always, the capacity of the cell, and also can lead to the lower cell resistance, or ionic conductivity, chemical stability, or ACI composition, and also flammability. So we can we can say that some self-healing materials not only perform the self-healing functionalities, such as like they recover the initial structure of the materials after crackings, or after like scratch or cut, but also they may give some additional benefits, like a low cell resistance or ACI composition, or improve the other properties of the materials, as like shown by this reference published in 2020, the authors applied interface layers between the anode and cathode before they have their solid state electrolytes, and they claim that by adding this interface layer, the cycle performance of the cell improves. But we have to make sure that it is very important that the improvement in the cell performance is because of the self-healing functionalities that we introduce into the cell. There is a lot of techniques that we use to characterize the self-healing functional groups. For example, like the authors in this reference, they use TEM. We also can use SEM, scanning electron microscope, and atomic force microscopy to observe the morphology and topography of the self-healing polymers in the batteries, which includes, we can study also their structure, size, distribution, and roughness level of the electrodes. In this literature, they combine two different types of polymer binders. And by using TM, they show how is the contact between the silicon particles and binders. Also, we can study the distribution and the structure of the polymeric binders, of which we expect that they have self-healing functions between these hydrogen bonds and borate ester bonds. And then we want to see how these functional groups are spread on the surface of the electrodes. And to characterize the self-healing functional groups also can be done precisely by using nuclear magnetic resonance spectroscopy and Fourier transform infrared spectroscopy, as shown by this reference in ACS Applied Material Interface. The authors use NMR spectroscopy to study the transformation of OH bonds into these functional groups by using proton NMR spectroscopy. Initially, we have they show a peak here between 10.5 and around 10.5 ppm chemical shift of the proton spectra, which correspond to the OH groups, and then this peak disappears after they change the functional groups into the sulfonyl groups, and then another peak appears at around 8 ppm. And later on, they change the hydrogen atom with lithium, and they show that this transformation by using FTIR, where these NH groups disappears in this type of polymer electrolytes. In other literature, the authors synthesized the polymeric binders, and they showed that the presence of OH groups in the polymers is also exists in the silicon electrodes. However, it is important to understand whether these functional groups bonds is breaking and forming during the self-healing process, which requires further measurements. And to characterize the self-healing functionalities, whether our self-healing materials perform as expected, some mechanical tests have been done by many authors in the literatures. For example, the author in these literatures perform tensile tests on their polymeric binders, where they apply tensile test until the polymer damage cuts here, and then after 1 hour, the polymers are connected again, and then they repeat the test. And other mechanical measurement that can be used is friction coefficient, reduced modulus, and hardness. And most of the papers also demonstrate the ability of the self-healing materials by using cut or scratch tests. For example, they perform scratch or cuts on their materials, and then they demonstrate the recovery of the initial structure after 2 hours, for example, or like after some times. So basically, these mechanical measurements can help us to understand the self-healing behaviors of the materials. However, we don't know whether the materials behave similarly in the battery systems. So we want to like really look at like what's happening in the battery system to the self-healing materials. One of the example is presented by this, by the authors in this literatures. They use like PVA binders for the silicon electrodes and like SPS binders for other silicon electrodes, and they cycle the cells after 100 cycles. They showed that the silicon electrodes with PVA binders show like a lot of cracks, while the other electrodes show like, that the electrodes can maintain the smooth surface. And other technique to evaluate the self-healing functionalities is by using electrochemical impedance spectroscopy, which can tell us like the change in the loss of the electronic contact in the cell during like cycling the battery. However, we need to remember that this data is also affected by other mechanisms such as electrolytic composition and so on. So it is like it is important to combine this ES measurement with other techniques. Evaluation of the self-healing ability are usually done by considering two important factors. The first of all is based on the time frame of the self-healing process, which means that the faster self-healing process the shorter time frame of the materials is the better for battery lifetime. Taking an example from this Nature Chemistry paper, the author shows the lithiated silicon electrodes after they place in, they observe how these lithiated silicon electrodes recover their initial structure by putting them, by exposing them into the SEM chamber. They could observe that the self-healing process can take place, but not fully complete even after 5 hours. And instead, actually, the surface of the sample changed maybe because of the bombardment of the electron beam in the SEM chamber. And another parameters of evaluating the performance of the self-healing ability is based on the long-term performance against repeating damage upon battery operations. In this case, self-healing efficiency and stability are crucial parameters when evaluating the self-healing ability of a long term. Here is the example from this literature. The authors show the tensile test of their materials, and until the materials is damaged, and then they wait for sometimes like for after 10 seconds, it recovers only like less than 50% of the initial strength. After 30 seconds, it could like self-heal better, and then after 3 minutes, it's perform like better recover ability, which means that it has like better healing efficiency. So like the healing efficiency is determined as the ratio between the retained value of the given property, such as the mechanical property of or ionic conductivity, or like something that we can measure with value, and then we compare this value before damage. For us who are working on the battery system, maybe we are quite familiar with like computation calculation of the Coulombic efficiency. So by comparing the healing efficiency and like time frame, like how many hours or how many minutes the self-healing process takes place, can help us to compare the performance of the materials. So like this is like quite similar when we compare with the cycle performance of the battery at different C rates and how much Coulombic efficiency that we obtain. So this will be like really help us to like compare between one and another self-healing materials. And self-healing stability is also another important parameters, which represents whether the polymer degrades or changes over time due to factors such as temperatures, humidity, fatigue, and exposure to reactive chemicals. And understanding the self-healing mechanism remains as the biggest challenge. Like we are trying to find better characterization techniques to understand the self-healing mechanism. And up to now, the characterization techniques are still limited, but in many papers, different self-healing mechanisms have been presented, such as in this literature. They combine PAA binders with polyrotaxans, and they propose the self-healing mechanism pulley concept. While the more we have pulley, the less we need force to retain the initial structure of the silicon electrodes, which is very interesting concept. But unfortunately, it is difficult to prove this mechanism. And computational method is useful to understand the self-healing mechanism, to predict the potential combination of different self-healing groups. Maybe we need to combine different self-healing groups, not only rely on one type of bonds. And also the computational method can help us to optimize design and to accelerate the development of self-healing materials. Here I summarize the characterization techniques that commonly employed and to barely employed techniques. For example, NMR and FTIR are widely used, and sometimes Raman or thermal analysis, thermogrammetry, the AC and the FGMD and XPS are quite relatively rarely used, and neutron scattering maybe will be the future potential for the characterization of the self-healing materials. And for the materials level, the evaluation of the sample are usually done by applying mechanical or physical tests, such as by showing an optic picture that using the scratch or cut test or tensile test, hardness and friction. And also some chemical tests of the functional groups. But for the electrochemical test level of the material is still rarely used. And especially in the battery cell level, we need to go further with long-term stability of the self-healing materials, and whether there is a degradation on the self-healing materials and their performance upon the application at high C rates and at high loading of the materials. So these are the characterization techniques that are still barely employed. And to evaluate the performance on the cell level of the self-healing materials, it is also interesting to see the self-healing mechanism by using operando or in situ measurements. Maybe we can take some measurement techniques that has been widely used, like NMR or FTIR or Raman, which also can be used for in situ or operando measurement. So in summary, the self-healing materials have the potential to significantly improve the performance and lifespan of the batteries, making them more reliable and efficient. And combination of measurements is required to assess whether the self-healing chemistries effectively address the challenge in the batteries. And the self-healing functionalities may provide different effects on the long-term stability of the battery performance, which is not always related to the improvement in the electrochemical performance, such as capacity retention, cell resistance, ionic conductivity, and ACI microstructure and other properties. But rather, it is very important to show the direct relationship of the self-healing materials and the long-term cycle battery performance. And evaluation of the self-healing efficiency and the given time frame is necessary to compare the self-healing functionalities between like different materials, so that we can like compare the performance and like evaluate the feasibility of these materials. And of course, future characterization techniques are still necessary to understand the self-healing mechanism and develop better self-healing materials. And I would like to acknowledge my supervisors, Christina Estrom and Jonas Minmark, and the funding sources for the project that I'm working on. And thank you very much for your attention.
Thank you very much, Wandy, and really these two very important presentations. So the floor is open for Q&A. We already have a couple, so please don't be shy and add what you are thinking. The first one is from Mehmet Gülkan. Is asking, do you have the possibility of any spectroscopic technique, especially XPS in situ examination like in this study? And there's a link to a publication. So I guess this is a question for Marta.
Yeah, so I had to look at the publication, and indeed, operando or in situ more than operando XPS are possible, with the limitation that as this technique requires a vacuum environment, a low vapor pressure materials, let's say, are needed. So liquid electrolyte are limited. I see Christina doesn't agree, but let's say it's mostly for solid state or like a system that are targeted for vacuum.
And I would like to then add that the new novelty is that you really have ambient pressure XPS, and that is now developing, and especially to look at the formation of the SEI. And I think this is a very interesting and difficult sort of advanced technique, but it's coming, and it's really more for liquid solid ones. But I agree with Marta that you indeed have a lot of important advancement in the solid state with traditional XPS techniques. So we see both. We are both right.
I'm always super excited when I see near ambient pressure studies on batteries, but I haven't seen yet on, let's say, realistic electrodes. I mean, but I might be not in touch with.
I have it in my pocket. I haven't shown it yet.
Then I'm waiting for it, because this is really exciting.
So great. So we will wait for many news in next future. Great. Thank you both. And the second question is for Wandy, I guess. It's from Zulkarnain of University of Kuala in Indonesia. The question is a very interesting presentation. For self-healing materials, are only polymers or also covers all classes of materials like metals, ceramics, and so on?
Yeah, there are many types of self-healing materials, as also has been presented by other presenters yesterday. Like I saw, like self-healing ionic liquid electrolytes and self-healing like electrodes, but my topic is really focused on the self-healing polymer for battery applications. So that's why my talk is only covers the self-healing polymers. But maybe like the one who asked for the question maybe could see the records of the yesterday seminars.
Exactly, it's what I wanted to add. Both the 2 days are recorded and will be available soon on Battery2030 webpage. So for sure there will be many opportunities. Is there any other additional question and answer? I take just one moment to ask something while maybe somebody want to add. You know, we are on this way on adding more and more smart functionalities to our batteries. So together with all these self functionalities, we are also adding sensors that can detect, sense many parameters, but also stimulate the self-healing properties. So my question is, by a characterization point of view, would this be, is the addition of sensors and all these functionalities disturbing the characterization or helping in the characterization methods, or maybe we have to start thinking to new characterization method and testing techniques for our future? What about your, maybe Wendy, as it is already here in the screen, and then Marta?
Yeah, I think
quite wide question.
Yeah, yeah, but, that's very good question. That we also should consider like the future, like future configuration of the battery when we are like considering the characterization, and of course we want to see the mechanism of self-healing, for example, by in situ. So I mean, we can see like the real-time mechanism of the self-healing functionalities of the materials, and like of course like the presence of how to say foreign species, like other than the main battery components. We need to consider also like it depends on the type of the measurements, and especially like for in situ or operando measurements, like such as by using NMR, which is non-destructive measurement, which is, I mean, very useful. Like for example, the presence of some metals may affect the acquisition of the data by the spectrometers. So like depending on the type of measurements and the type of materials that are present in the battery, it also affects us like in like selection of the characterization techniques.
Thank you. Marta, what about
something, yeah.
your point?
So for sure, there are like some techniques that have some limitation. For example, also some spectroscopy technique like XPS, they might require, for example, a specific cell design. So we might be limited on that sense, like to add extra sensors. But with the idea that we need to go like more and more towards in situ operando, like real devices. For example, with high energy scattering, we can measure like real batteries, like 18650 prismatic cells. This is not a problem. And actually, there's a lot of research on how the sensor, how the glass fibers are perturbing the cell. Like, is it like, I don't know, increasing the degradation, or like, is there any thermal gradient because of the sensor? So that's something that actually has to be taken into account and is being investigated. But for sure, like thinking about new techniques that can be applied for studying, let's say, how the sensors are perturbing, these are always welcome. Like, I think like this is never, like, I don't think that anyone would say, oh, no, we are not like looking for new answers.
Yes, but how the new techniques can be open, or maybe there are something that we are not thinking now, but they can appear on the scene very soon, coupling with these smart functionalities. I don't know, it's just, I'm not expert, so it's a question for you. There's a question from the audience, from Badri Hazard. Thank you for a nice presentation. I'm Badri Hazard for NTUST in Taiwan. What are your opinions on the crystallinity characterization of self-healing polymer electrolytes for lithium-ion applications, lithium battery applications, sorry. About the crystallinity. Who wants to start? Marta, you are here. Maybe
I can answer from the characterization point of view. Crystalline materials are the easiest to study because we're scattering, like we don't have any problem, especially, for example, if they come from a polymer that, for example, doing self-healing properties, or like when it's activated, it goes from amorphous to crystalline. This is like super easy to investigate. then I'm not a specialist at all on polymer, on self-healing or self-healing properties. So I don't know, let's say, how it will affect. But from the characterization point of view, this is like the easiest to study.
Do you have anything to add, Wendy?
I fully agree with Marta.
Sure. Very clean signals, high and well localized. Easy
May I comment?
to find. Let me check. So I close between.
May
Please,
I
sure. You're welcome.
just comment on this question, because the question could be, I don't know, that if you have a self-healing polymer that goes crystalline, how much will that affect the ionic conductivity of the whole polymer system? Because we know that the ionic conductivity is better in the amorphous regions of polymer electrolytes. So it's this question. So I think that it's a very good question. The problem to study the crystallinity of self-healing is probably that the amounts of the self-healing additive is quite low. So we can't use typical diffraction techniques and so on. So we really need to think about the characterization there too. Sorry to interrupt, but I get inspired by your presentations.
We have some scattering techniques which are coupled with tomography, which can really look at nanoscale where, for example, the crystalline phases are appearing. And this can give like some answer from the engineering point of view, because if, for example, the crystalline phases are formed more like, I don't know, close to the tablets or close to the, I don't know, to the walls of the battery, this can be an answer. And there are like, I mean, the more we advance on the characterization point of view, the more answer we can give to let's say, to the engineers or to the chemists who are actually making the batteries. And so I think that there has always to be this combination from, let's say, the battery, let's say, producer that are like industry or research labs, and the characterization people who needs to interact to solve exactly these kind of problems.
I completely agree. And I think what you mentioned with its tomography is interesting, because there you also see the combination that you build up an X-ray tomography and do simultaneous measurement with electrochemistry and neutrons is a very, very new and very exciting field that will probably go into this. You're absolutely right. Sorry, I will hide again.
No.
Thanks for your comments, Christina.
Thank you. It's very useful. I have the floor. I take the floor for that very last question. And then we close the meeting. Or if there are other questions, please ask. I was also combined to this question on crystallinity. For example, mechanical properties can be strongly affected from the different amorphous or crystalline states, maybe for a polymer, but also for other materials. How these mechanical properties are very important, in particular if you consider cylindrical cell, when you have to bend the electrodes. So adding functionalities adds some degree of complexity to the system, or in particular also for these mechanical properties. What about the characterization? Is it possible, for example, combining the mechanical properties with the characterization method to see how these smart functionalities can perform? Marta, I see you. Sorry, I don't know if you can answer.
I don't really have an answer, but for sure, for example, we can look at the displacement or like of materials inside of the batteries with tomography, and this will give us for sure some mechanical information. But I'm not an expert on mechanical. I don't know, like if there are more specialized technique, like on stress strain. Maybe Wendy was showing something on stress strain. So
yes, in fact, now I was going to Wendy.
Like actually, like mechanical test has been widely used to characterize the self-healing polymers. But we don't know like what is happening. I mean, really the mechanism during the healing process, like whether the bonds in the polymers are really like forming and breaking. So we cannot get like this information by using the mechanical test, but for sure we can make the correlation between the mechanical test and the cell performance, for example, and maybe by combining other characterization techniques, which still I don't know what are the techniques exactly. We will be able to measure and get better information regarding to the self-healing functionalities of the materials. And here I would like to highlight the importance of interdisciplinary and multidisciplinary research. Maybe because most of us are chemists or material scientists, maybe people from biology or from civil engineering, they know better how to characterize, and they know better characterization techniques that can be combined to understand better materials. So I think multidisciplinary or interdisciplinary research will be very important for us, and especially the self-healing functionality research is quite relatively new and opens a big opportunity for collaborations, I think.
Thank you. I fully agree. So this multidisciplinary makes battery sexy, as Christina is wishing. So I do not see any other. No, there's one question. Sorry, a comment from Samson Lai of IFE. It says it seems electrochemical dilatometry might be useful for characterizing self-healing properties. So this is more a comment. Thank you. I agree. So, I don't know if some of you want to add something on this. If not, I also thank who is now writing a wonderful workshop, Bertrand Grass from Indonesia. So let me say that we had a lot of attendees out is make us proud also to do that. So thank you very much to Marta and Wendy for your very great presentation. And I think it was very important, let me say, session inside all these workshop that now closes. And so I give the floor to Christina, who reached us, and so for the final remarks. Yes, so thank you very much, everyone. See you at Battery 2030 General Assembly.
Yes, thank you so much on behalf of Battery2030.
Please.
And I would really like to thank Sylvia for putting this together, and all of you that have been speaking these 2 days. And I'm very pressed that we have an audience coming from all over the world. Some people are really waking up in the middle of the night to listen to you. And I think that's a great achievement. So welcome to Uppsala, the 9th and 10th of May, to our annual meeting. And congratulations to this really well done workshop. So see you soon somewhere. And I can tell you that we have an excellent seminar that you should not miss, the 30th of March, where Christine Persson from Berkeley will talk about modeling. So if you want to learn more, look at our webpage on what's coming up next. So thank you so much, all of you.